All right, hello everybody. Working on implicit differentiation. In other words, how do we take a derivative when your x's and y's are all mixed up in the problem? I'm going to remind you all of our good friend the chain rule. And the chain rule says that if you've got a function inside of another function, you do the derivative of the outside function with the exact same inside, and then you multiply by the derivative of the inside function. So that's the chain rule. Implicit differentiation is the same idea. We just are using the letter y to stand for some other undetermined function. So when I take the derivative of a function involving the letter y, I take the derivative of the outside, and then I multiply by the derivative of the inside, which I will just denote as y prime. You could also write dy dx if you like that notation more. Sort of personal preference. So here's our function, x squared minus xy plus y squared equals 3. Every time I see a function of x, I just do a normal derivative. Every time I see a function of y, I make sure that I keep this chain rule idea in mind. So here's my derivative. The derivative of x squared, it's just a function of x, so I just get 2x. The derivative of xy is a product rule. F is x, and g is y. So if I go f prime, that's 1 times g, y, minus f, x, g prime, y prime. So this is f prime g, f, g prime. And then y squared, this is the one that most people mess up on. It's a function squared, so I do 2 times the original function times the derivative of the function, y prime. This is also another common error. The derivative of 3 is 0. When you're doing implicit differentiation, actually when you're doing any derivative, you're always doing it to both sides of the equation. You're taking the derivative of each piece. It's just that often when we do explicit differentiation, we've already solved for y explicitly. Okay, let's move all of our not y prime stuff to the other side. So if I subtract 2x and add, or I could do it this way. I can move this stuff over here. Doesn't really matter which side of the equation you move things to. So if I move that stuff over, my left side is just 2x minus y, and my right-hand side is xy prime minus 2y y prime. The reason I hesitated and redid it is because I looked at what they requested me to make the answer in terms of, and so I saw 2x minus y, and I just realized I would like to keep this block right where it's at. It's fine if you move it to the other side, you just have it written backwards. Both the terms on the right-hand side have a y prime in common, so I can factor out y prime to have x minus 2y. And then to get y by itself, I just divide both sides by x minus 2y. And I should say to get y prime by itself. And now I have proved the thing they asked me to prove, that y prime is that. Y prime is the same as dy dx. Okay, and on part B, find the coordinates of the points where the tangent lines are parallel to this, that, and the other thing. On each of those, you need to think about what does y prime tell you and what does it mean to be parallel to a tangent line. Well, y prime tells you the slope of the tangent line. So if I want to be parallel to the line y equals x, I want my slope to equal 1. In other words, I want my slope, which has a crazy formula, this is my slope, and I want it to be equal to 1. So 2x, oh that was weird. So there we go. Sorry about that, a little trip out. So 2x minus y equals x minus 2y. If I subtract x and add y, I get x equals negative y. Now, this tells me that whenever x equals negative y, I am parallel to y equals x, but I don't have the points yet until I plug it into my original equation. My original equation tells me the points that are on the graph. My derivative tells me the slope at those points. So I know when x equals negative y, my derivative is equal to 1, and so I plug those points in. So I'm plugging in negative y for x, so negative y squared minus negative y times y plus y squared equals 3. The negatives cancel out here. The negatives cancel out there. So I have 3y squared is 3. So y squared equals 1. Y equals plus or minus 1. And remembering that x is negative y, this gives me 2 points where y is positive and x is negative 1, and where y is negative 1 and x is positive 1. So in other words, when we're at this point right here, where we're at 1 comma negative 1, and at this point right here, we're at negative 1 comma 1, and you can actually see visually that that's got a slope of 1. So does that, so they're parallel to the line that was given. Really similar process for the next one, where it says we're parallel to the x-axis. That means a slope of 0, so you just say set your derivative equal to 0. I'm going to go skip onto this one where it says set the parallel to the y-axis, so that'd be like a vertical line. And think about what happens if you have a vertical slope. A vertical slope means rise but no run, so you're dividing by 0. It means that your tangent line is undefined. It means that the slope of your tangent line is undefined. It means that your denominator had to equal 0. So let's clear everything. Let's look at this. If our denominator equaled 0, we just get x equals 2y. We do our substitution into our original equation, 2y squared minus 2y times y plus y squared equals 3. So let's see. 2 squared is 4, so we have 4y squared minus 2y squared plus y squared is 3. That is, I guess, 3y squared equals 3. So again, we get y equals plus or minus 1. But in this case, x is equal to 2y, so we get plus or minus 2. So we're at the point here where 2 comma 1, and here negative 2, negative 1, and you can see that each of those points is a vertical tangent line because I made the denominator equal to 0. So that's just a good example of implicit differentiation. Please let me know if you got any questions. Happy to help out.